Okay, so we looked at the variable partition scheme for memory allocation, and we concluded by saying that there's a problem with that idea of putting processes into holes, and that problem is called fragmentation, right? So in this segment we'll take a closer look at what that is. So fragmentation basically means your memory is broken into chunks or fragments. So if you go back to the picture here, you have your memory, and ideally you would like to put everything continuously like this, right? So when your one process, let's say process 8 has moved, ideally you would want to put P2 over here and then all the free blocks together, so that you can continue to allocate smoothly. But we cannot do that reshifting every now and then. Every time a process leaves, you cannot take the next process and put it up here, because that would mean context switch, that is costly and time consuming. So you cannot keep shifting a process's location. It's like same like shifting residence, right? You cannot keep shifting your residence every now and then. It's a tiresome task, it's a time consuming task to pack at one place and go unpack, arrange things at another place. Shifting once or twice probably is fine, but every time every now and then if you're going to keep shifting a residence, it's not a feasible option. It's going to be a waste of time, money, energy, all of that. Same thing with processes. Every time a process is cleared, you cannot take the next process and put it immediately beside the previous one, because that's a waste of time and resources which you could be using to do something useful on the computer. So we don't generally do that shifting, so we let the holes be and we try to fill the holes with newly incoming processes. Now the problem with that is the memory is broken down into small disjoint chunks which are called fragments, right? So if both of these had been like next to each other, maybe they would have, in this picture, last picture I'm talking about, there's this blue chunk and this blue chunk. If they had been together as one continuous block, maybe you could have fit one nice big process in there. But because they are separated into two chunks, you might not be able to do that. So that problem is there, which is what we call fragmentation. So in that we have two types, external and internal fragmentation. So external fragmentation, when you have enough total memory to satisfy a request, but the available spaces are not contiguous, they are fragmented into a number of small holes. So we will take a pictorial example. So you have your memory goes from 0 to 10 for the sake of simplicity, no more. 0 to 4 is taken up by P0, 4 to 6, those two spaces are free. 6 to 7 is taken up by P1, again 7 to 10, those three spaces are free. So you have 2 free spaces here, 3 free spaces here, which means you have 5 free units. And P5, which is newly incoming, needs 5 units of memory. So technically speaking, you have enough memory to be able to accommodate this process, but they are not contiguous, they are two separate fragments. So you cannot allocate memory to P5. P5 will have to wait until one of these fellows finishes and leaves, although there is actually enough memory, enough space in your memory to accommodate P5. Because that space is not continuous, this P5 is being made to wait. So there's a delay involved, right? So this kind of thing is called external fragmentation. You have enough total memory to satisfy the request, but the spaces are not contiguous, they are fragmented. So what we do to solve this problem is, you break the so external fragmentation is that. Now to solve this, you can do two things. One is you can do compaction. Compaction is where you reshuffle all the allocated units together to create continuous free blocks. So 0 to 4 was P0, right? And then we had P1, which is just 1 unit. So in the 6 to 7, this P1, I will move it to 4 to 5 immediately after P0. So 0 to 4 is P0, 4 to 5 is P1. Then I have 5 to 10. I have 6 free places. So I have enough to accommodate P5, so I can put P5 here. So this reshuffling which we talked about is called compaction. Now you can do that, but as I said, context switch is costly, so that is not always a feasible option to solve external fragmentation. So instead we have to look for another solution. Generally what they do is, you break the physical memory into fixed size blocks and allocate memory in units based on block size. So what that means is, instead of allocating exactly as much as a process wants. You break your memory into segments and you give so many segments to each process. So here if you see, P0 needed 4 spaces, you gave exactly 4. P1 needed 1 space, you gave exactly 1. Instead of doing that, you set some block size, allocate that to every process. So for example, here let's say you have 14 spaces, you divide it into 2 blocks of 7 units each. The first 7 units go to P5, the next 7 units go to P0. Like that if you allocate. Now your P5 needs only 5 units, so it will take up the first 5 units. The next 2 spaces are free, but that has also been allocated as the address space of P5. So now although that is free, it cannot be used up by another process. Now see, why do we do this? See, this is a problematic thing, of course. Like P5 needs only 5, then why are you giving it 7? Is because external fragmentation can be avoided. So when you give it each process small chunks specific to how much space they need, then when that process finishes and leaves, it is going to give you small chunks or fragments which you cannot use, right? But whereas if you allocate 7 units now to P5, how much ever P5 is using, once it finishes and goes, you have 7 units free. So there you can allocate for another process. So that external fragmentation problem will be avoided. But what happens here is, P5 needs only 5, you are forcefully giving it 7 units, it will take up space for 5 units and the remaining 2 units will be empty. So there again, maybe some process which needed only 2 units could have been put there, but because 0 to 7 has been allocated as the address space for P5, it has to remain unused until P5 finishes and leaves. So this kind of fragmentation, where the memory allocated to a process is slightly larger than the requested memory. So requested memory here was 5, allocated was 7. So 7 is slightly larger. In such cases, that difference is the internal fragment. So this 2 units becomes an internal fragment. So that's the idea of fragmentation. So see, technically you could say, we tried to solve one fragmentation, we ended up creating another type of fragmentation. Yes, like most problems in computer science, most problems in operating systems, you might have realized now, it's not about finding an absolute solution. The idea is generally to find a good trade-off, because whichever direction you go in, there's going to be a benefit and there is going to be a price to be paid. So the idea is to find a middle ground, a good enough trade-off such that you get as much of both benefits as possible and you have to pay as little of either price as possible. So that's the idea of memory allocation and the 2 types of fragmentation. And so the overall, the challenge to the OS here is allocate memory in such a way that both types of fragmentation are minimized to the maximum extent possible.